Imagine a tiny creature, no bigger than the palm of your hand, walking upside down on any surface, effortlessly defying gravity. It climbs walls, ceilings, and even glass, without slipping a single time. This is the gecko, a small, unassuming lizard, yet one of nature's greatest engineers. For millions of years, geckos have evolved a secret technology built into their feet, one that allows them to cling to surfaces with incredible strength, yet release and move with perfect agility. One day, a curious scientist, Dr. Emily Carter from the United States, noticed something extraordinary. While observing wildlife in her lab, she saw a gecko effortlessly scale a glass wall, moving in ways that seemed almost impossible. How could such a tiny creature, with such delicate feet, adhere to vertical surfaces without glue, tape, or claws? She realized that the secret was not magic, it was physics, and more importantly, nature's genius engineering. Dr. Carter began studying geckos closely. Using microscopes, she examined their tiny toes, discovering millions of microscopic hairs called setae. These hairs split into even smaller structures at the nano level, creating an enormous surface area that allowed the gecko to adhere using van der Waals forces, a type of molecular attraction that humans rarely notice in everyday life. The more she studied, the more fascinating it became. These tiny hairs could generate enough force for the gecko to hang upside down, yet the gecko could release its grip and move without effort. Dr. Carter thought, if nature has solved this problem so perfectly, can we replicate it? Can we take this tiny creature's secret and use it to create materials humans have always dreamed of, sticky, reusable, and incredibly strong? As she pondered this question, a vision began to form in her mind. This was not just about geckos, this was about turning nature into technology, about letting a tiny lizard teach humans how to design adhesives, robots, and materials that could revolutionize engineering. Little did she know, this small observation would spark a journey combining biology, nanotechnology, and lasers, a journey that would lead to breakthroughs nobody had imagined. And so, it all began with a gecko, tiny, unassuming, and silent, yet ready to inspire the future of technology. What Dr. Carter didn't know yet was that this tiny creature would challenge her imagination, push the boundaries of science, and ultimately show the world how nature could teach humans to create materials more advanced than anything we had built before. After witnessing the gecko scale a smooth glass wall, Dr. Emily Carter felt a spark of curiosity unlike anything she had experienced before. She realized that this tiny lizard was performing feats that human engineers had been trying to replicate for decades. But how? What secret did these minuscule creatures possess that allowed them to defy gravity with such elegance? Dr. Carter began studying geckos closely. Using microscopes, she examined their tiny toes, discovering millions of microscopic hairs called setae. These hairs split into even smaller structures at the nano level, creating an enormous surface area that allowed the gecko to adhere using van der Waals forces, a type of molecular attraction that humans rarely notice in everyday life. Using high-powered microscopes, Dr. Carter discovered the microscopic structures on the gecko's toes. Millions of tiny hairs, called setae, branched into hundreds of even smaller tips at the nanoscale. It was at this scale that physics performed its magic. These nanoscopic hairs created a network of van der Waals forces, a type of molecular attraction that, while invisible to the human eye, was powerful enough to hold a gecko's entire weight, even upside down on a glass ceiling. Dr. Carter spent weeks observing the patterns, measuring adhesion strength, and testing how geckos adjusted their grip. She realized that this wasn't just a biological marvel, it was a blueprint for human innovation. The gecko's foot was a natural adhesive system, perfectly designed over millions of years. The more she studied, the more ideas began to form in her mind. If nature had solved this problem with such precision, could humans replicate it? Could we create surfaces that stick without glue, adhesives that are reusable, robots that climb walls effortlessly? The possibilities were endless. But Dr. Carter knew that traditional methods would not work. Simple molds, synthetic adhesives, or even 3D printing could not capture the intricate nanostructure of the gecko's feet. That's when inspiration struck. Laser technology. What if we could use lasers to scan and replicate the microscopic structures of the gecko's feet? Lasers could measure features at the nanoscale, etch or print patterns onto synthetic materials, and potentially recreate the natural adhesion that had amazed her for so long. The first experiments were simple yet revolutionary. Dr. Carter and her team aimed a precision laser at a tiny gecko toe sample, carefully mapping every hair and branching structure. The lab was quiet, the only sounds were the faint hum of equipment and the scratching of pens as her team recorded observations. With every scan, they uncovered more secrets: how the hairs aligned, how the angles affected grip, how flexibility combined with strength to create perfect adhesion. It was not an easy journey. Initial attempts to transfer these patterns onto synthetic materials failed repeatedly. The adhesion was too weak, or the surfaces were too rigid. But with every failure, Dr. Carter learned something new. Slowly, patterns were adjusted, laser intensity fine-tuned, and the combination of material pattern began to produce results that mimicked the gecko's natural abilities. By now, Dr. Carter realized that she was standing at the beginning of a new era. Nature had given humans a blueprint for a technology that could change engineering, robotics, and even medicine. From a small observation of a tiny lizard's foot, a bio-inspired revolution was about to begin. As she looked at the gecko climbing the side of her lab wall once again, she whispered to herself, "This is just the beginning. One day, lasers and nature will work together to create materials and machines we can only imagine today." And with that thought, the journey into laser-inspired, gecko-inspired super materials officially began. After weeks of meticulous observation, Dr. Emily Carter realized that human tools alone could never recreate what nature had perfected over millions of years. She needed a technology precise enough to capture the tiniest details of the gecko's microscopic hairs, structures invisible to the naked eye. That's when the team turned to lasers. Laser technology, long used in precision engineering and medical procedures, had the ability to scan surfaces at a microscopic level. Dr. Carter's idea was simple in theory but revolutionary in practice: use lasers to measure every curve, every split, and every tip of the gecko's CD, and then recreate these structures synthetically. The first day in the lab, anticipation was high. The team positioned a single gecko toe under a precision laser scanner. Slowly, line by line, the laser mapped the surface, recording millions of tiny features. On the monitor, an intricate network of hairs appeared, branches so fine they were invisible to any conventional microscope. The team gasped. Nature had outdone any human-made design. But observation was only the first step. The real challenge was transferring this blueprint onto synthetic materials. Early attempts failed spectacularly. Plastic surfaces were too rigid, adhesives didn't hold, and the laser sometimes damaged delicate nanopatterns. Dr. Carter knew that if she wanted to succeed, she had to combine precision laser technology with advanced materials science. Little did she know, this tiny observation would spark a revolution in robotics, adhesives, and materials science. But that story continues. Part 2 is in the next video. Don't forget to watch it.